Hello physics students. So in the last two physics videos, we learned how to calculate the various aspects of a projectile's motion. Like for example, how long a projectile spins in the air, how far it travels horizontally, maybe how high it rises to its maximum peak. So we crunched a lot of numbers, we learned the techniques, and we were able to analyze the various parts of projectile. What we're going to do in this video though, is we're going to step back and just look at the patterns, which means we're not going to focus in on any numbers, we're not going to crunch any numbers. We're just going to think about bigger, smaller kind of things and figure out certain patterns that exist, particularly for projectiles that you launch at an angle like this, maybe an arrow shot up like this. So, projectile motion patterns. Suppose I've got a bow and arrow that launches the arrow at 100 meters per second every time if I pull it all the way back. What I'm going to do is I'm going to first launch that arrow at 20 degrees. So I go like this, tilt it up 20 degrees, I let it go. Then I'm going to launch it again at 70 degrees. So I pull it back and I tilt up 70 degrees like this, I let it go, the arrow fires away, 100 both times. Note that the angle 20 and 70, those angles add up to 90. That's a key feature of what we're going to be talking about here. So I've drawn a little vector diagram here. Of course, I could find these x and y components using sine and cosine. I'm not going to do that again. I'm not crunching numbers. We're just going to look at the patterns. But if you did, you would find that this had an x velocity of 94 and this had a y velocity of 34 if you shot at that angle. If you shot at 70 degrees, it's the same triangle reworked around 20-degree angle up here. You'd get these same numbers, but the 94 would end up on the y component of velocity, and the 34 would end up as the horizontal component of the velocity. So what does this mean? The first thing is that this one spends more time in the air, because remember, from the last video, the part of the velocity that determines how long something spends, a projectile spends in the air, is how fast it's launched upward. Throw something up gently, it comes back down. Throw it up real hard and it's going to spend a lot of time in the air. So this one spends more time in the air than this one because of the y velocity. If you wanted to calculate the exact number of seconds, remember it's because of this formula. And so what you would do is plug in 34 initial, negative 34 final, negative 9, you get a time. But the point is, with less velocity, we get less time. Here, with more y velocity, we get more time. This one's going to spend more time in the air. What does that mean for how far these arrows go? Well, how far the arrows go in the x direction is given by this formula, d equals vit. What we have here is more x velocity than we have over here. We have less x velocity of 34. However, with more velocity and less time, that ends up being the same horizontal distance as less velocity with more time. The effects balance each other out. These two arrows land at the same location. I could summarize that with the following diagram, but before I move on, I'm going to create a pause to allow you to catch up if you need to copy these notes down. Let's move on. So here's the pattern, same velocity to my arrow, different angles. This is a drawing of this pattern here. For 20 degrees, this lands in very little time right at this point, this orange parabola here. I launch at 70 degrees, going to spend more time in the air, but come and land at the same exact point. And the pattern, the reason for that is if the two launch angles, first of all, the speed has to be the same, but if the two launch angles add up to 90, the two projectiles will go the same horizontal distance. Of course, the larger angle, more time, as I already said. The other pattern that's true is, yes, this spends more time. Well, the way to make a projectile, this arrow, spend the most possible time in the air is if I direct all the velocity straight up. Then it'll get the most hang time. So 90 degrees goes the highest and spends the most time in the air. But it doesn't go anywhere. The arrow will go up and straight down, land at the same spot. And, by the way, it'll go the same distance if I launch the arrow instead of 90 degrees, I launch it at 0 degrees at ground level. of course it's not going to go anywhere because it's already on the ground. So notice 0 degrees and 90 add up to 90, so they go the same distance of 0. If I launch at 40 degrees instead, what you would find is the 40 degrees would go further than the 20 and land here. But if I take that arrow and instead of 40, I go up to 50, what I would find is the 50 degrees, as we said, spends more time in the air but lands in the same exact spot because 40 plus 50 equals 90, as I already mentioned. Okay, so add up to 90 degrees, go same distance. And the final point is that if you want the projectile, this arrow in this case, to go the furthest possible horizontal distance, something's really far away and you're trying to hit it, you pull back and you launch at 45 degrees, and that represents the largest possible horizontal range for the projectile. But I just want to add, that's only true if there truly is no air resistance. If in real life you're shooting an arrow, there is air resistance. It turns out that that magic number for going the furthest is a little bit less than 45. Maybe it's 40 degrees or something like that. So air resistance, you want to go a little bit less than 45 to get the maximum range. But again, in the Regents curriculum, 45 maximum horizontal range. So these are the little facts you need to know. I'll create a pause to allow you to copy these down. Okay, so that's it for today. Remember, we just learned some basic patterns like this, more and more time in the air, same angles, same range, maximum range of 45. I hope you enjoyed the video. I'll see you in the next physics video.